1 integration using integration by parts method. We'll jump right on in and look at the formula for integration by parts. To use this formula, what we'll need to do is identify u and dv in the original integral. And then we will compute du and v and then use this formula. So we will be using an acronym to decide what to let u be, and then whatever is remaining in the integral, all of it, is going to be dv. And then we will use this formula. So the goal is that finding u is something easy to find the derivative of, and dv is easy to integrate. That's the goal. So also, I want you to keep in mind that this is undoing the product rule. This comes from the product rule. I'll just put reverses. The product rule, probably not the correct notation. Okay, let's begin. So we have this integral x sine of x dx. So using this acronym LIPIT, we choose L for logarithms, I for inverse functions, inverse trig functions, P for polynomials, E exponential, and of course T trig functions. So the I is just for the inverse trig, okay? So that's what we'll be using the acronym LIPIT. So do we have in this integral a logarithm? No. Do we have an inverse trig function? No. We have a polynomial. So what we're going to do is we're going to let u be x and dv be everything else, which is the sine of x dx. Okay? So really what we have is the integral of u dv. Okay? So let's go back over here and find du, which is just dx, and we'll find v. And the antiderivative of the sine of x is the negative cosine of x. So let's go. The formula that we have above here is the integral of u dv is equal to uv, which is x multiplied by negative cosine x minus the integral of v du, which is a negative cosine x dx. Let's take a moment to clean it up. Okay, all we have left is to integrate the cosine of x, which is just the sine of x, plus c. And that's it. Now sometimes we might have to use this method more than once. Let's see what happens. LIPIT. I don't see a logarithm. I don't see an inverse trig function, but I do see a polynomial. So we're going to let u be x squared. So dv must be e to the x dx. Now, look how easy v is to find. It's just e to the x, because the derivative of e to the x is e to the x. Du is 2x dx. Probably need to move that over a little bit. Okay, let's go. So we have the integral of u dv. This is a good time to check. Yep, x squared is u, and e to the x dx is dv. So I have the integral of u dv. Really good time to check to see if you have those. Okay, so we have a formula that says that that's uv minus the integral of v du. I should have probably written that in number 1. And that's just x squared e to the x minus the integral of 2x e to the x dx. Well, everything's fine with the x squared e to the x, but what do you notice? Yep, you guessed it. We'll integrate by parts again. So, using Lipit, again, we have a polynomial. So we're going to let u equal 2x, so dv must be equal to e to the x dx. Du is 2dx, and v is e to the x. Let's go. That's equal to x squared e to the x minus, I'm going to tell you right now, parentheses are everything, and let me explain why. We are subtracting this integral, and this integral is parts, and parts has a subtraction in it. So we are going to be subtracting all of this. Extremely important to remember those parentheses. So minus, let's just write the formula, uv minus the integral of v du. There's no problem with writing that formula. Minus, now let's go ahead and see what uv is this time. 2x e to the x. And what is this next one? That's right, it's a plus the integral of v du. So 2e to the x dx. Well, we're almost there, because now we can say that that's equal to x squared e to the x minus 2x e to the x plus 2e to the x plus a constant, because the integral of 2e to the x is 2e to the x. Now, you could see that if I gave you x to the 15th power e to the x, you might be integrating all day long through breakfast, lunch, and dinner. So we do need a quicker way. So let me introduce you to what we call the tabular approach. The tabular approach is helpful with these repeated integration by parts problems. But first, we do need to talk about when we can use the tabular approach to integrate. When we can use that, okay? So I don't know why I have a question mark there. So when can the tabular approach to integration by parts be used? When one function integrates to 0 and the other repeats or cycles. In other words, when the other one never goes away. You can't get rid of it. I'm going to actually write that. Can't get rid of it. Kind of funny. Okay, so you know what? Let's just jump right in. We definitely have an integration by parts. This is the same as number 2. Look. Okay? This is the same integral. But I want to see if I can use tabular. Will x squared integrate away? Yep, the integral of x squared is 2x. The derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. Yes, I've got one function that integrates to 0. And we all know that I should have said here when one function has derivatives. Oh my. To 0. And the other repeats and cycles. Okay. Probably didn't explain that very well. Okay, so we already said that x squared, when you continue to take the derivative, will eventually get to 0. And e to the x, when you integrate that, or take the derivative, you can never get rid of it. Okay? So we're going to use parts. So we're going to make a table, and this is the tabular method for parts. So this left column we're going to use is going to be the column for the taking the derivative. And this one we're going to integrate. So that you need to write those functions. So x squared is the one that when I continue to take the derivative, I'll eventually get 0. And e to the x, I will be integrating. Okay? So here we go. Leave a little space and keep your rows nice and neat. The derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. That's how you know when you need to stop. Take the derivative all the way to 0. Now, start integrating the other function. And repeats and cycles while integrating. I didn't do a very good job of explaining that, but you get it. Okay, so the integral or the antiderivative of e to the x is e to the x. And the antiderivative of e to the x is e to the x. And the antiderivative of e to the x, e to the x. Okay? So now, there's just one more thing. Plus, minus, plus, minus. Start with plus and alternate all the way down. And then I want you to draw diagonal arrows. Okay? And we're going to multiply these together. It's probably better not to circle them because there's just too much written there. So what we're going to say is this integral is x squared e to the x minus 2x e to the x plus 2 e to the x plus a constant. Is that what we got up here? Yes. So, I mean, you can decide if you like tabular or if you like the parts formula. But I want to also mention that tabular is parts. So I don't want you to think if you're choosing methods, if I asked what method would you use, partial fractions, completing the square, or integration by parts, and you're thinking, well, that choice isn't there because you would use tabular. Tabular is integration by parts. It's just a different approach and a much nicer approach. Okay, let's keep going. So we have x squared, ln of x. Let's write our acronym, LIPET, L-I-P-E-T, and right off the bat, we have a logarithmic function. So that was easy. We're going to let u equal the natural log of x, and dv is everything else, which is x squared dx. So we now have the integral of u dv. And that integral is uv minus the integral of v du. So du is 1 over x dx. And v, now we need the antiderivative of x squared, which is 1/3 x cubed. And this probably up here should say, while finding the antiderivative. Yep, it is late. So, and the other function cycles or repeats while finding antiderivative. Because we won't be integrating these, we're not using a constant, we're just finding antiderivatives. Okay. So, why can't we use tabular here? The natural log of x doesn't ever go away, and it doesn't cycle or repeat. Cycle meaning sine, cosine, e to the x, e to the x, e to the x. But the natural log will never go away. Anytime you see a natural log in one of these integrals, you're going to have to use the parts formula. Okay? So, let's go ahead and write uv, which is 1/3 x cubed times the natural log of x minus the integral of 1/3 x cubed times 1 over x dx. And you'll like this method because there's always some nice algebra included. So this is minus 1/3, let's clean this up, x squared dx. Okay, we are almost there. It's equal to 1/3 x cubed natural log of x minus 1/3 times 1/3 x cubed plus a constant. And that's just equal to 1/3 x cubed ln of x minus 1/9 x cubed plus a constant. Now, we have been working with definite integrals, if you can see, indefinite integrals. But now what happens when we have definite integrals? I'm going to tell you right now, one of the biggest mistakes is students forget to stop after they find uv. You see, there's no integral left. Once you get to uv, you're finished. To go ahead and plug b in and then subtract, plugging a in, just like we've done with our previous integrals. You need to stop and do that. And then you can proceed with this integral, okay? Let's give it a try. What do you notice? Yep, we can use the tabular method. X will differentiate to 0, and the sign of x will cycle as we find antiderivatives. So this is very, very nice. So we don't need to use our acronym or anything. We're going to find the derivative here, and we're going to find the antiderivative here. X, 1, and 0. So not much there. And the sign of x. Now, the antiderivative of the sign of x. What do we take the derivative of and get the sign of x? And it is the negative cosine. And then, what do we use here? The negative sign. And you can go ahead and check these. The derivative of negative cosine is negative sign is negative cosine. And then the derivative of negative cosine is the sign. So it's really nice. Big, big important thing. Plus, minus, plus. We multiply along the diagonals. Remember, this is a definite integral. So we will have to first integrate as an indefinite integral and then apply the limits of integration, okay? So we have negative x cosine of x minus the sine of x evaluated from 0 to pi over 2. Okay, so let's go ahead and plug pi over 2, negative pi over 2, cosine pi over 2, minus the sine of pi over 2. All of that minus 0. I'm just going to put a 0 in because plugging in 0 for that x, that's gone. 0 minus the sine of 0. Well, the sine of 0 is also 0. So this is gone. Okay? So now we have the opposite of pi over 2, and then the cosine of pi over 2 is 0, minus the sine of pi over 2, which is 1. And I don't know why I have a negative sign. Oh, a negative times a negative. Yep. Yep. And yep. And then also, I think this should have been a plus. And so, equals 1. And that was a nice one. So now, let's go ahead and look at this challenge problem. Okay? So what we want to do is rewrite this problem, this integral. And we're going to write what we would normally write in an equation form. So it'll make more sense in just a minute. We'll go ahead and write limit. I don't see a logarithm, an inverse trig. I don't see a polynomial, but I see an exponential. So we are going to let u equal e to the x. dv must be cosine 2x dx. V must be the sine of 2x. Now the antiderivative of the cosine of 2x is 1/2 the sine of 2x. Now let's talk about that. The derivative of the sine of 2x is 2 sine of 2x. So that 1/2 will cancel the 2 in the denominator out, and we will get the cosine of 2x. So that probably needs to be practiced a little bit. And then du is e to the x dx. So now we're going to go ahead. I probably should have written that a little further to the right, but that's okay. I'll write it down here. The integral of e to the x, cosine of 2x dx, is equal to uv, which is 1/2 e to the x sine of 2x, minus the integral of v du, which is 1/2 e to the x sine of 2x. Let's see. uv minus the integral of v du. Yeah. Okay. 1/2 e to the x sine of 2x dx. Okay? So now, what's the problem? The problem is, here we had an integral of the cosine, and now we end up with an integral of the sine. We need this integral to have a cosine in it so that we can bring it over to the other side of the equation. If you don't quite understand that, that's okay. What we want to do right now is parts again. So let's go ahead, and this time we're going to let u be e to the x, and we can go ahead and keep this 1/2 on the outside. So dv is cosine 2x, sine 2x dx, and v now would be 1/2 negative cosine 2x. the derivative of the negative cosine is the positive sign, and then we need that 1/2. So du is e to the x dx. So let's see what we got. We want to keep this in equation form, the integral, and you'll see why in a moment. 2x dx is equal to 1/2 e to the x sine of 2x minus 1/2. And now I'm going to use a bracket, because remember, we're going to use parts for this integral right here. And parts has a difference in it. Okay? So let's take uv, which is negative 1/2 e to the x cosine 2x. So uv minus the integral of v du. And that's going to be a plus now, because minus a minus, 1/2 e to the x cosine 2x dx. Now it looks complicated, but no worries. So we have the integral of e to the x cosine 2x dx is 1/2 e to the x sine of 2x. Now we're going to distribute this negative 1/2. So that's a positive 1/4 e to the x cosine 2x. And here we have another 1/2. So that's a negative 1/4 e to the x cosine 2x dx. So now what we have is that we can add that to the other side of the equation. So that makes it really, really nice. And now here is, I'll highlight it in green. Oops, I forgot that integral. So we have a negative 1/4 of these, and we have 1 over here. So I'm going to add a 1/4 of that integral. So you can almost think about it over here is 1 plus 1/4 of those integrals. So we're going to have 5/4 times the integral of e to the x cosine 2x dx, and that's equal to 1/2 e to the x sine of 2x plus 1/4 e to the x cosine 2x. Now, what they asked us to solve for was this integral. That was the original integral. So all we have to do is multiply the other side of the equation. So we will multiply both sides by 4/5. And that's how we can remove the 5/4. And so 1/2 e to the x sine of 2x plus 1/4 e to the x cosine of 2x. And we might as well go ahead and finish this up. That would be equal to 2/5 e to the x sine of 2x plus, it looks like 1/5 e to the x cosine of 2x. And there you have it. So let's just go over this real quick. The reason why we had to use integration by parts twice is we had to cycle from a sine to a cosine in that integral, because the cosine is what we were wanting to solve for. And it's almost like having this term in the on the other side of the equation, or it is, and then you can bring it over there and solve for it, okay? So that is a challenge problem. There's probably a good chance you won't see that except for a bonus, but it's really, really good to work that out and have you see that. Okay, that concludes this topic.